All right, so our review topics for the day are on carboxylic acid syntheses. So we're going to talk a lot about carboxylic acids and their derivatives. So we need to remember how to actually make these. One of the ways we'll be using organometallics as well. So a topic near and dear to my heart. We'll have 3 learning objectives, 2 of which are actually recalls, meaning you've learned these before, either earlier in this class or in 2301, as you see in chapter 12.12. So we'll go over those again, as carboxylic acids are very important functional groups, and they can be made into a lot of other functional groups that we're interested in. All right, let's go ahead and launch into this. So our first learning objective, which is 19F, so learning objective 19F is going to be this, recall the 2 Ps, so no mechanism needed, just the reagents and starting materials and predicting the product. So the 2 Ps of benzylic CH oxidation, so turning a CH bond into a C oxygen bond to form carboxylic acids. And this is a little bit of a throwback here, because you learned this back in 2301 in chapter 12, right? So we weren't super concerned in 2301 with too many mechanisms. So. All right, so we used a benzyl CH bond. So benzyl meaning that it needs to be not a phenyl CH bond, a benzyl CH bond. So what are these CH3s here? So this is called the benzylic position. Right, these CHs. So if it was a phenyl CH bond, it would be on the benzene ring. But if it's benzylic, it's the carbon attached to the benzene ring. We learned we could add in an oxidant, which is potassium permanganate, KMnO4. So I'll write that name out for you. KMnO4, that's potassium per, the prefix per means you have as many as you can, so permanganate. That means you have as many oxygens on this as you can have. All right, and so let's look at where manganese is. This is probably the most commonly confused element. In the periodic table, a lot of people think it's magnesium, which is element 12, but it's not. It's in the D block. Manganese is abbreviated Mn as element number 25. It's a transition metal. So I'm a transition metal chemist, so I always really like to see transition metal reagents. And what this is it's an oxidant. All right, so if it's an oxidant, we're going to get rid of CH bonds or replace those with CO bonds. All right. So let's see what we get out here. Our learning objective says we're going to form a carboxylic acid. That is, in fact, what we will do. All right, so here's our carboxylic acid. All right, so this is just a 2 Ps. You just need to remember this reagent, which is potassium permanganate. It's a bright purple color, which is kind of fun. Transition metals have electrons in their d orbitals. That's why they're in the D block. And when we expose those to light, especially with first row transition metals, we get a lot of energetic transitions going on, and you see really beautiful colors. So many people, that's a realm of inorganic chemistry, and they like inorganic chemistry because all the really beautiful colors that form. So it's a deep, deep purple color. All right, so we've already seen this before. No need to really dive deep here. We just want you to know this reagent so you know how to make a carboxylic acid, and we've learned a few other reagents to do that as well in this class. So this is learning objective 19G. This is again a recall. So we've seen these before. So we're going to recall the two P's. So again, no mechanism needed of alcohol. Spell that wrong. And aldehyde oxidation. Of course, this is going to be to form carboxylic acids, because that's what our next chapter is going to be a lot about. We're going to see this over and over again in this chapter as well. And so this is in 16.9. Sometimes we call this the Jones oxidation, the one that I'll talk to you about, but I don't love names, but you might see this in Alex. All right, so you will recall when we had this primary alcohol, meaning we had two CH bonds off of it, we could add in our potassium chromate. And we also needed a little bit of acid as a proton source and water as a source of our OH. All right, and so at the end of the day, we can go ahead and get our product here. So all of these oxygens, the oxygen is going to come from your chromium, the hydrogen is going to come from the acid, your double bond is going to come again from the chromium, and this is just our carboxylic acid product. So I'm not going to worry about drawing it in color where each of the components come from, because it's a little bit less relevant when we don't need to know the mechanism. All right, so we could take this primary alcohol because we had two CH bonds. We had a secondary alcohol. Recall, we could never make that because we wouldn't have enough CH bonds to turn into carbon-oxygen bonds for our carboxylic acid. But the other starting material we can start with is an aldehyde, because an aldehyde is just one oxidation state above our alcohol, right? So we've sort of already gone halfway in this situation. So we can add in the exact same conditions, our potassium chromate with our acid and our water, and we can get out our carboxylic acid product. All right, so just like potassium permanganate, potassium chromate is an oxidant. All right, so let's take a look at where chromium is in the periodic table. So we see that it's very close to manganese. So it's element number 24, a first order transition metal. So the things that we can recognize about these reagents is they have transition metals bound to a lot of oxygens in both cases, right? So this is helping us to understand that these are in fact oxidants. Okay, so we've learned these before, and we'll need these because we're going to do a lot of carboxylic acid chemistry and a lot of carboxylic acid derivative chemistry, where instead of having an OH, we're going to have an O something. Or instead of having an OH, we're going to have a carbon bound to a nitrogen or a chlorine. These are all carboxylic acid derivatives. All right, so we do have one learning objective today, though. That's going to be new for us. It's not going to be a recall, and it's going to be a one with a mechanism. So this is learning objective 19H. This is going to be the 4 P's for the formation of carboxylic acids, you might guess. I'm going to form these from carbon dioxide, CO2, and organometallic reagents. And this is in 19.11. All right, so we've seen organolithiums and organomagnesium reagents add to a lot of carbonyl compounds, like aldehydes and ketones, but our electrophile in this case is going to be CO2. All right. And CO2 looks like a pretty, you can abbreviate it, of course, CO2. You have to draw it out. But I drew it out for you to help you understand how this is potentially going to react, right? So just like we have our carbonyl compounds like aldehydes and ketones, now we have a carbon bound to 2 oxygens. So that really means we have a good delta plus or partial positive charge at that carbon, because we have our electronegative oxygens on both sides that are pulling electron density away with those delta minuses or partial negative charges. All right. So when we think about this, the electron density is being pulled away from our carbon twice. Right. So CO2 is not a super reactive molecule. We breathe it, right? We breathe it out. It's in the air all around us, but we can utilize it with a very reactive nucleophile, something like an organomagnesium or organolithium reagent as our nucleophile. All right. So we know where the bond should form here, because we know where our delta plus is, and we know our organomagnesium and organolithium reagents have a carbon in that R group that is a delta minus. All right. So let's go ahead and see if we were to add that R group, what we would have initially is a carboxylate. Oops, it should be double bonded. And then we would have some sort of either lithium or magnesium counterion, depending on which one we used, right? Draw that positive charge a little closer between the two of them. So that would be our counterion. And so just like when we use organomagnesium and organolithium reagents, we need to use an aqueous workup in the second step, so that we end up not with a carboxylate, but with a neutral carboxylic acid. Then we can go ahead and use this in further reactions. Right, so this is just really, really similar to what we see in the aldehyde or ketone reactions, right? We have a really strong nucleophile. We know it's a strong nucleophile because our carbon, element number 6, is far more electronegative than magnesium or lithium, which are all the way over in groups 1 and 2 on the periodic table. So that's why we know the delta minus is on our carbon. All right, let's take a look at the mechanism for this reaction. I think hopefully we should be able to kind of be comfortable with this by now, because it's very similar to what we've seen before. All right, so we're going to take our organomagnesium reagent. I'll use a Grignard in this case as our nucleophile. We'll add in our CO2. So CO2 is dry ice. You can just drop a little pebble of dry ice into your reaction. And that's how we actually do this in the lab. Our electrophile. All right, so we know from mechanisms, we know that our electron density is going to start from the metal carbon bond. All right, this is where electron density is starting from. We're going to go ahead and have that electron density add into that electrophilic carbon where we had previously shown we have that delta plus. And then, of course, we need to break 1 CO bond so that we don't have 5 bonds to carbon. So it's just a very short 1-step mechanism. In the first step, before we add in our magnesium, or sorry, our water to quench it. In this case, we have a magnesium bromide plus. Right, it's just that one arrow for this mechanism. And then we'll go ahead and do a deprotonation of our acid using an arrow from our oxygen to our hydrogen, breaking that OH bond of H3O+. We get down to our final product. All right, so even though it's a P4 mechanism, it's something that we've seen before, right? So this was just like if we had an aldehyde or a ketone, we would have gotten out an alcohol product, not a carboxylic acid, but the arrows are the same. So first arrow we have is nucleophile attacks the electrophile. The delta plus site, and then we have to have a second step, you'll recall, as protonation of the carboxylate in the workup. All right, so this is a pretty simple mechanism for today. Is this something that we've seen before? All right, so we can do a little practice problem here, and you can think about how you would make this compound, all right? So let's just do a practice. All right, so we could think about this particular compound here and think about ways we could make it. All right, so I'm going to give you a few seconds to think about that. See if you potentially have a couple of different ways that you could make it based on what we learned today. So I'll give you a few moments to think about that. So if you're kind of stuck here, I would take a look at the carbon here and see what kind of carbon is there. Is this something that we could potentially use a organolithium reagent, for example, and add it to CO2? So if we did that, we would be breaking the bond here, for example. So in this case, we could have an organolithium reagent, organomagnesium plus CO2. Would be a nice way to make this carboxylic acid, right? So we also learned benzylic oxidation. This doesn't look like a very good candidate for benzylic oxidation, right? We don't have a benzyl group because we don't have a phenyl here, right? So instead, let's think about a different way to make this other than our organolithium reagent plus CO2. And what if we thought about a chromium oxidation? What if we thought about turning this molecule, instead of breaking a carbon-carbon bond, what if we had a primary alcohol there? We have two CH bonds, so we could add in our chromium, right? And that would allow us to get to the final product. Or we could even think about if in the lab we didn't have this particular alcohol, we could even think about if we had the aldehyde, because the aldehyde would work in this case as well, right? So we could do that plus our potassium reagent, potassium chromate. Right, so sometimes it can be a little bit intimidating to think about molecules, but we kind of think about the different places that you can break bonds, the different things we know how to do. We know how to make this carboxylic acid a number of different ways. We identify we can't do anything benzylic, so that leaves us a couple of other options, right? So there's a couple of different ways that we could go ahead and try to make this molecule. All right, so that brings me